Thank you so much. I'm Lieutenant Derek Benham. I'm a resident at Naval Medical Center San Diego, and this was a project that was combined between us at NMCSD and Madigan Army Medical Center, so thank you. This is validation of a miniaturized handheld arterial pressure monitor for guiding full and partial REBOA use during resuscitation. Okay, this slide's not working. Oh, there we go. This work was funded by the Telemedicine and Advanced Technology Research Center at the United States Army Medical Research and Material Command through the AMED Advanced Medical Technology Initiative. Otherwise, we have no financial disclosures. Non-compressible torso hemorrhage is frequently seen and very frustrating aspect of trauma care, especially in modern warfare. TCCC has an advanced resuscitative care algorithm that involves using whole blood as well as REBOA for control of this hemorrhage. However, as noted in a JSOM article in 2018, there is a need for better technology suitable for the austere environment to help guide REBOA placement and to monitor and control a partial REBOA as well. Our current endovascular occlusive devices include the standard ER REBOA, which is a non-titratable endovascular occlusion for the aorta, and then the partial REBOA, which is allows the choice of full occlusion versus partial occlusion, and the maintenance of flow, some flow distally. This is a schematic of how the partial REBOA works. There's a spine balloon in addition to the occlusion balloon that allows for limited flow distally past the area of occlusion. As in the prefill stage, there's 100% of baseline flow, and then after the balloon seats and makes the wall apposition, there is a decreased flow up until it has full occlusion. This requires a very arterial line setup, which is very cumbersome. There's pressure bag, transducers, monitors. There is a device called the Compass, which measures a mean pressure in a system, and it's handheld and miniaturized. Our question is this reliable arterial pressure data? Our objective was to evaluate the accuracy and precision of the Compass versus arterial pressure monitoring with both ER REBOA and partial REBOA. In a combined IACUC-approved protocol between Naval Medical Center San Diego and Madigan Army Medical Center, 40 Yorkshire swine were used in a 4-phase validation and precision study. Phases 1 and 2 analyzed the accuracy and precision of the Compass with ER and partial REBOA in uninjured animals, and phases 3 and 4 did the same with a severe hemorrhagic shock model. Laparotomy was performed and the following exposures were made. Left internal iliac artery was exposed, and through this a sheath was placed for the REBOA, and a distal arterial line and Compass was placed through this sheath as well. The right iliac artery and vein were isolated to be used for our injury, and as the superior mesenteric artery was isolated and a Doppler flow probe was placed here. The bladder was catheterized with a Foley catheter. A left anterior thoracotomy was performed through the 8th intercostal space for aortic exposure, and a Doppler flow probe was placed around the aorta here. Bilateral neck cut-downs were performed, and the right internal jugular vein had a Swan-Ganz catheter placed, the right common carotid artery had an arterial line, and the left internal jugular vein had a cordis central line placed. For our data collection, we used arterial lines and the Compass. The proximal arterial line was through the right carotid. Proximal Compass was on the distal aspect of the REBOA. The distal arterial line was through the sheath in the left iliac artery, as well as the distal Compass. Our injury model involved a 20% total blood volume controlled hemorrhage, which was weight-based for each swine, and an uncontrolled hemorrhage, which consisted of a laceration to the right iliac artery and vein. Resuscitation followed TCCC guidelines, and when MAP fell below 40 millimeters of mercury, 250 cc's of Hextend were initially administered, followed by the 20% total blood volume blood transfusion. Crystalloid was then administered if the MAP stayed below 40. For the accuracy testing, phases 1 and 3, phase 1 being the non-injury model and phase 3 being the hemorrhagic injury model. Each phase had 5 ER REBOA and 5 P REBOAs. At time 0 minutes from injury or from the start of the experiment, ER and P REBOAs were fully inflated. At 15 minutes, the ER REBOA was taken down completely, and the P REBOA was deflated to a target flow rate of 0.7 liters per minute. At 60 minutes, there was complete deflation of the partial REBOA. For the precision testing in phases 2 and 4, phase 2 was the non-injury model and phase 4 was the hemorrhagic injury model. Again, we used 5 standard REBOAs and 5 partial REBOAs per phase. At 0 minutes, these were again fully inflated, and then there was titration to specific flow rates using both of the ER and P REBOA. So we attempted 1 liter per minute, 0.7 liters per minute, 0.5 liters per minute, and 0.3. These goal rates were held for 15 minutes before going down to the next flow rate. Our data collection included the included proximal and distal measurements of the compass and arterial line, and the Doppler flow probes had the flow measured. Our data analysis involved correlations and then a bland-Altman analysis as well. For our results in the accuracy testing of the non-injury model, we showed a correlation coefficient of R equals 0.94 for the proximal measurements and 0.8 for the distal. And in the precision, we had an R value of 0.98 in the proximal and 0.89 in the distal. All p-values were significant here. In the hemorrhagic injury model, we showed the proximal value of 0.98 and the distal in 0.99 for accuracy. And for precision, the proximal was 0.97 and distal R was 0.95. Again, these were all statistically significant as well. For our proximal bland-Altman analysis, we showed extremely low bias with bias equaling 1.9. And in the distal bland-Altman analysis, we again showed extremely low bias of 0.8. So the compass is a handheld miniaturized device that we showed does measure mean arterial pressure. It is both accurate and precise when compared to arterial lines in non-injury and hemorrhagic injury models, and has extremely low bias. In conclusion, compass is a technology that may help bring REBOA forward without the need for a cumbersome arterial line setup. This enhances the critical care abilities in forward deployed settings and is a critical care, something that can help bring forward critical care to closer to the point of injury. Thank you, and again, thank you to our colleagues at Madigan Army Medical Center and to my co-authors as well, and I take any questions.
Very good. Great presentation, Dr.
Thank you.